Dr. M.C. Sundaraja. He completed his undergraduate studies from Madurai Kamaraj University and went on to complete his master's in structural engineering from the same. He is a doctorate from Anna University and he's also done his postdoctoral fellowship at the Queensland University of Technology, Australia. He has more than 17 years of experience in the teaching profession and he has also published papers in 39 international journals, 7 national journals, 27 international conferences and 51 national conferences. He has so far published 124 papers in various journals. He went on to receive the Best Research Paper Award from IFERP, a unit of VVERT and NIRE on 4th April 2015. He has also received Outstanding Faculty Award from the Venus International Foundation Faculty Award, VIFFA, in the year 2015. Currently, Dr. M.C. Sundaraja is now working as an assistant professor in Tyagarajar College of Engineering, Madurai.
Welcome to UGC lecture series on B architecture. In the previous lecture, we started discussing about the design of staircase, that is different components of the staircase and what are the types of staircase, and also we started finding the width of the different components of the staircase by start designing with the help of one problem. In this lecture, we are also going to design the dog-legged staircase by using the component which is predicted in the previous lecture. So, here the problem here it is the service stair of an office building is to be located in a staircase hall measuring 3000 millimeter by 5000 millimeter. The vertical height of the floor is 3000 millimeter and the thickness of the slab is 125 mm. The stair is supported on 230 mm thick walls, use M2D and Fe415 as material. Lie load on the slab is 3 kN per meter square. Draw the cross section of the staircase showing the reinforcement details. So, here also we are going to find these are all the things, that is fixing of dimension of the components, effective span of the slab, load on the base slab, loads on the landing slab, loading diagram and bending moment using the loading diagram, and find out the effective thickness of the slab from the bending moment, and also we are going to find out the main steel as well as distribution reinforcement for the bending moment, and we are also going to check the tip of the slab against deflection. Finally, we are going to see the reinforcement detailing. So, in the previous lecture, by using these components, we are going to start designing the dog-legged staircase. Here the size of room which is given was 3000 millimeter by 5000, which was supported on 230 mm thick wall. So, the effective size of room is 5230 mm by 3230 mm. So, here we have assumed the thickness of the staircase is thickness of the riser is 150 mm. Then we have found the number of steps as 12 numbers, and using 12 numbers we have found the exact thickness of the riser, and also we have assumed the thickness of the tread as 275 mm. Using the tread thickness as well as the number of steps, we have calculated the horizontal length of the base slab, that is 3300 millimeter. That is within 5000 we need to accommodate the width of passage as well as the landing. So, here we have found the horizontal length of base slab is 3300 and remaining length has to be adopted for the passage and the mid landing. So, I have fixed the width of mid landing as 900 mm and the remaining width has been fixed for the passage, that is 800 mm. So, we have calculated the horizontal as well as the vertical dimensions of the components of the staircase as well as the steps. Now, we need to start calculating the load, that is load calculations. Before that, first we need to draw the loading diagram. The center to center of the support here it is 5230 millimeter, and we have left some space for the base slab, that is 3300 millimeter, is correct, and the remaining 9000 plus the half of the support is 1015 millimeter, and here it is 915 millimeter, 800 plus 115, that is the loading diagram in meter, here it is 0.915 meter and 3.3 meter and 1.015 meter. So, here the full length is the effective length is 5.230 meter. Now, we need to find out what is the loading on the base slab, which must be normally greater than the loading on other portion, that is such as passage as well as the mid landing. Now, load on base slab. First, dead load. Now, I am going to assume the thickness of the slab as, based on my experience, I am assuming the thickness of the slab as 230 mm. Normally, it has to be assumed from L by D ratio, that is equal to 20. So, D is equal to L by 20, that is 5230 divided by 20, that must be equal to 261.5 millimeter. But I have assumed the overall thickness of the slab as 230 mm. So, self height of base slab in slope, that is in slope formation, that is 0.23 into 25, that is equal to 5.75 kilonewton per meter square. So, here I need to find out what is the self height of the base slab in horizontal position. The horizontal position, this again multiplied by, that is square root of r square plus t square divided by t. It has been found that is, this is a base slab. Now, this is called as t, sorry, riser, and this is t, and this is r squared plus t square. So, the horizontal component I need to find out, cos theta must be equal to r, that is t divided by square root of r squared plus t square, which must be equal to 5.75, that is equal to 5.75 into square root of r squared plus t square divided by t. So, if it is, you know the riser, we know the thread, we know the thread and the denominator. Now, here if it is if it is multiplied by this factor, this has been again slightly increased 6.56 kilonewton per meter square. So, for load calculation we need to take the self height of the slab in horizontal position. Next one, self height of steps. Normally above the base slab we can start constructing the steps. Steps is normally the thickness. Normally the riser is 151.1 millimeter. This is the thing we have calculated. So, here the average thickness is 0.151 by 2, that has to be again multiplied by the unit weight of the materials which are used for the construction of the steps. Normally we are using brick as a material for the construction of the steps. So, the unit weight is 20 kilonewton per meter cube, that is it has to be multiplied by 120, it will become 1.5 kilonewton per meter square. This is the way of calculating the weight of steps. Average weight, average height of the step is 0.15 by 2. Now, next one is dead weight of steps we have calculated, then weight of floor finishing. The floor finishing which is normally taken as, that is the thickness of the floor finishing is 0.025 and its respective unit weight is 24. This will be 0.6 kilonewton per meter square. Next, assume the weight of handrail. The handrail which is normally made by using wood as a material, aluminum as a material, steel as a material, and stainless steel as a material. It may be vary from 0.6 to 1 kilonewton per meter square. So, here I have used 0.6 kilonewton per meter square. These are all the dead load which is acting on the base slab, that is self height of the base slab in horizontal. Above the base slab we are constructing steps, above the steps we are constructing the floor finishing. After floor finishing we are fixing, or we are fixing the handrail. These are all the dead load which is acting on the base slab. So, total dead load on base slab, that is equal to say 6.56 and 1.51 plus 0.6 and plus 0.6, that is equal to 9.27 kilonewton per meter square. Next, the live load on the slab, this is given in problem. that is WD, this is WD, WL is equal to 3.0 kilonewton per meter square. Now, then total load on waste slab, that is equal to 12.27 kilonewton per meter square. This is the total load on the waste slab, that is this one is 12.27 kilonewton per meter square. Now, we are going to find out what is the load on the landing and passage. Load on landing and passage. First one, dead loads. So, self height of the slab. The self height of the slab is normally the slab thickness we have assumed as 0.23 into 25, which is equal to 5.75 kilonewton per meter square. This is the self height of the slab, and self height of floor finish. The floor finish, which is normally 0.025 into 24, which is equal to 0.60 kilonewton per meter square. These are the two dead load which is acting on the landing and the slab. So, next one is live load. Live load on slab is 3 kilonewton per meter square. Now, total, this is taken as WL and this is taken as total dead load, that is total dead load WD is 6.35 kilonewton per meter square. 6.35 kilonewton per meter square plus 3 is 9.35 kilonewton per meter square. Total load on landing, that is 9.35 kilonewton per meter square. So, using this I am going to draw the loading diagram. I have already draw the loading diagram, but here I am again draw this, and here we are having, and this one is 0.915 meter and this one is 1.015 meter and this one is 3.3 meter. So, totally it is 5.230 meter. So, it is 12.27 and this one is 9.35 and this one is 9.35. Now, we need to calculate the maximum bending moment on this slab. So, now bending moment calculations. So, to find the first we need to find the reaction R A and R B. To find R A and R B, for that I am taking moment about A, taking moment about A. So, R B into 5.23, which is equal to 9.35 into, so R B into then 5.23, 9.23 into 0.915 into 0.915 square by 2, sorry 915 by 2 plus 3.3 into 12.27 into 0.915 plus 3.3 divided by 2 plus the 9.35 into 1.015 into 0.915 plus 3.3 plus 1.015 by 2. This is the way to calculate the reaction at the support B. R B here it is 29.36 kilonewton. Now, we need to calculate R A. So, R A is equal to the total load acting on the slab minus R B, that is 9.35 into 0.915 plus 12.27 into 3.3 plus 9.35 into 1.015 minus R A is 29.36, that is equal to R B is 9. R A here it is, sorry, R B is 29.18, R A is 20, R B is 29.18, RA is 29.36 kilonewton. Now, we need to calculate the maximum bending moment. Normally, in the case of maximum bending moment, the maximum bending moment occurs where the shear force is 0. So, we need to first find out what is the distance of point of 0 shear from the left end or from the right end. So, the distance of point of 0 shear from left end. So, RA minus 9.35 into x minus 12.27 minus 9.35 into x minus 0.915, which is equal to 0. From that, I want to find out x. So, here I am assuming that the x occurs at the center portion of the beam. So, I am taking x from the left end, R A into x minus 9.35 into x, R A minus 9.35 into x minus the 12.25 minus this load into the distance from the center of the slab, that is x minus 0.915 is equal to 0. So, here x is equal to 2.60 meter. Using x, I am going to find out what is the bending moment. So, the maximum bending moment which occurs at a distance 2.60 meter from the left end. This is the point where the maximum bending moment occurs. Now, I am going to find out the maximum bending moment. The maximum bending moment is equal to R B into RA into 2.60 minus 9.35 into 0.915 into 2.60 minus 0.915, that is, listen. So, 9.35 into this distance. So, from the point where the CG of this load occurs, this is the CG of this load, that is 0.915 by 2 minus 2.60 or 2.60 minus 0.915 by 2 minus 12.27 into 2.60 minus 0.915 into 2.60 minus 0.915 by 2. So, here R A is 29.36. Now, the maximum bending moment is 40.12 kilonewton meter. This is the way of calculating the bending moment in the base slab using the loading diagram. Next, mu, that is ultimate moment, 1.5 into 40.12, that is equal to 60.18 kilonewton meter. Using the bending moment, I am going to find out what is the effective thickness of the slab or effective depth of the slab, that is D. Consider 1 meter width of the slab, and by equating mu to mu limit, that is mu is equal to mu limit is equal to 0.138 FCK base. It assume that we are assuming, it means that we are assuming our section is a balanced section. So, D is equal to square root of mu divided by 0.138 FCK B. So, that is equal to 60.18 into 10 to the power 6 divided by 0.138 into 20 into 1000, that is equal to 147.66 millimeter, which is less than 202 millimeter. So, we have kept it as 230 millimeter, D as I think that 230 millimeter, and small d is 202 millimeter, which is less than 202 millimeter, hence safe against flexure. Now, we need to find out the reinforcement. So, I am going to keep d is equal to 230 mm and small d is equal to 202 mm. Now, area of reinforcement. In the case of area of reinforcement, we are going to find out main steel as well as distribution steel. Main steel should be found against maximum bending moment. So, mu equal to 0.87 F5 AST into d minus 0.416 XU. where XU is equal to 0.87 Fi AST divided by 0.36 FCK into B. So, here we are considering 1 meter width of the slab, this may be equal to 0.05 AST. By substituting in this expression mu here it is 60.18 kilonewton meter. 60.18 into 10 to the power 6 is equal to 0.87 Fi AST into D minus 0.416 XU, that is 0.87 into 415 into AST into D is 202 minus 0.416 into 0.05 AST. Now, by simplifying this expression, I am getting an quadratic equation AST square minus 9711.33 AST minus 8.01 into 10 to the power 6 is equal to 0. So, by solving this quadratic equation, I am going to get at 2 roots. I am going to select minimum root since it is singly reinforced section, that is 910.10 millimeter square. Now, here we have found the area of reinforcement, then I am using 16 mm diameter bar, number of bars. In this case, we are finding out the number of reinforcement, that is total area of reinforcement is 910.10 millimeter square divided by 1 area of 16 mm diameter bar, that is equal to 4.53, that may be equal to 5 numbers. 4.53 must be equal. So, provide n plus 1 number of reinforcement, that is 5 plus 1, that is 6 numbers, that is n plus 1 numbers of 16 mm diameter bar. This is the area of reinforcement required provided for the base slab. So, AST provided here it is, that is 6 numbers of pi by 4 into 16 square, which must be equal to 1206.36 millimeter square. This is the main reinforcement. Now, we need to find out the distribution reinforcement. Distribution steel, that is AST is equal to 0.12 percentage of gross area of concrete, that is into 202, that is equal to 242.4 millimeter square. This is the area of distribution steel. If you use 8 mm diameter bar, by using 8 mm diameter bar, spacing of reinforcements, this is provided in a perpendicular direction of the main reinforcement. Spacing is pi by 4 8 square into 1000 divided by 242.4, that is equal to 207.37 millimeter. So, hence I am adopting 8 mm diameter bar at 175 mm center to center. And finally, we need to check the thickness of the slab against deflection. After this one, we are going to draw the reinforcement detailing. So, L by D ratio is equal to, it is a simply supported slab, this has to be multiplied by, that is modified by multiplying with the modification factor. For this, we need to find out the percentage of tension reinforcement, that is 0.60 percentage. So, the stress in steel is Fs, that is 0.58 Fi into AST required divided by AST provided, that is 0.58 into 415 into AST provided, here it is 1206.36, 1206.36, AST required is 910.10. So, the stress in the steel, here it is 131.60 Newton per millimeter square, and the modification factor, here it is 1.8 by referring figure 4 of IS 456-2000. Now, so here D is equal to L by 20 into modification factor. So, L here it is 5230, that is the length of room, the length of the slab, 20 into the modification factor is 1.8, that is equal to 145.28 millimeter, which is less than 202 millimeter. Hence, it is safe, but it leads to uneconomical Hence, we need to redesign the slab by reducing the thickness of the slab further, but it is safe against fracture as well as the serviceability. Now, I need to draw the flight of one reinforcement required for one flight of the dog-legged staircase. So, here the main reinforcement is normally which is provided at the bottom. This is 6 1 that is 7, I think that it is 6 numbers of 16 mm diameter bar, and here at the bottom reinforcement has to be extended into the base slab at the top. So, this length must be equal to development length of the reinforcement. So, LD, which is normally equal to pi sigma ST divided by 4 into tau BD, we need to find out. And here also the same reinforcement, that is the main reinforcement, has to be extended into the base slab at the bottom for a distance of 150 mm. This is as per IS 45, sorry, SP 34. We need to refer SP 34 1987 for drawing the reinforcement detailing of the slab. Then, in order to keep this main reinforcement with the proper spacing, so the distribution reinforcement has to be provided. This is 8 mm at, I think, 175 mm center to center. We need to see this. So, the thickness of the slab we have designed here, it is 230 mm. The thickness of the slab here, it is 230 mm. The perpendicular dimension of the slab is 230 mm. And the main reinforcement is 6 numbers of 16 mm diameter bar, and the distribution reinforcement is 8 mm diameter bar at 175 mm center to center, 8 mm diameter bar at 175 mm center to center. Now, we come to the end of this lecture. Let us summarize this lecture. We have seen the design of a dog-legged staircase, which is used for any type of building, that is office building or public building or any residential building. In this case, we have fixed the dimensions of components of the staircase, and we have started designing by finding the effective span of the slab and load acting on the base slab and the landing slab. And by drawing the loading diagram, we have found the bending moment. By using the bending moment, we have found the thickness of the slab as well as the reinforcement required for it. In the case of dog-legged staircase, we have found 2 different reinforcement, one is main steel, another one is distribution steel. Finally, we have checked the thickness of the slab, which is found against the bending moment against the serviceability condition also, that is under deflection. And also we have seen the reinforcement detailing. In connection with this lecture, the questions may be: design a dog-legged staircase for a residential building having a staircase room of size 1200 mm by 4500 mm, subjected to a live load of 3 kN per meter square. Consider other dead loads also. Draw the cross section of the staircase showing the reinforcement details. This is the design of dog-legged staircase. So, we must know how to calculate the load on the base slab as well as the landing slab. So, the load on the base slab is much different from the load on the landing slab. So, using this one, we need to find out the bending moment and we need to find out the thickness as well as the reinforcement required for it. And in connection with this lectures, we need to refer the following IS codes as well as the books: IS 456-2000 plain and reinforced concrete code of practice, and IS 875-1987 code of practice for design loads for buildings and structures, and another important handbook, that is the special publication 34-1987, which is used for drawing the reinforcement detailing of the base slab. And the well known book which was written by S.N. Sinha, that is Reinforced Concrete Design, which was published by Tata McGraw-Hill Publishing Company. And another books, that is Ashok K. Jain, that is Reinforced Concrete Design, Reinforced Concrete Limit State Design, which was published by Nemchon Brothers, Roorkee. Let us complete this lecture. Thank you very much.